Bismillahirrahmanirrahim. Welcome to the third video about the kinetics of radioactive decay, and this is about the separation or the analysis of the radioactive mixture by using the Semilog paper. So actually, this video is about the application of the previous two videos in which you have learned about the kinetics and the half-life. And about the Semilog paper, now we will be using the kinetics, and we will apply the knowledge on the Semilog paper, and we will get the analysis to separate the radioactive mixture. So again, this is the Semilog paper as explained before. The x-axis is the same, having the same interval, but the y-axis interval are different. It is based on the baseline. So this is the first baseline starting with the 100, and it will be the 200, 300, 400, 600, 700, 800, 900, and the 1000. So this will be the first cycle, and the second cycle will be starting in the similar way. So I'm not going to go to the in detail about this one, because if you need, you must watch the video number 2, which is available on my YouTube channel. So here I am going to describe how can we analyze if there are more than one radioactive nuclides are present, because the activity is coming out in the form of the like any integration, alpha radiation, beta electron capture, or the gamma radiation. So if there are more than one nuclides are present, then how can we analyze them, how many nuclides are present there, and what are their initial activities, and what are the half-life of the radioactive nuclides. So these are the three main objectives in which I am going to describe in this video. So the first simple is because this is the integrated equation. Again, there is no need to use the to take the log natural of n or a, the number of radioactive nuclides or the activity of the radioactive nuclide, because we are using the Semilog paper and it is already having the log axis. Y is already having the log axis, so you can directly put the value on the y-axis and get the data by using the Semilog paper. So let's suppose this is the, if you can obtain a state line, that means if and there is only one state line is there, that means one radioactive nuclide is present. So one state line is indicating with the one radioactive nuclide, and this is the, because we are using the first order kinetics. So if you fit the data and the data is like in this, that means there is only one nuclide is present. So let's see what is happen with the composite decay. That means more than one nuclide are present. Then this is the first line. It is shown by the A. This is the composite decay curve. That means this curve is indicating that there is more than one nuclide are present, because if there is only one nuclide is present, then you can only get the state line. So this curve is indicating you that is there are more than one radioactive nuclide are present. Now the question is, how can we analyze either there are two radioactive nuclides or more than two radioactive nuclides? So the process is very simple. I will explain in detail in the next slide, but here I'm just going to show you how can you analyze. So this will be the overall activity you have plotted on a Semilog paper. And the first, because here you can see there is a straight line, and you just extrapolate this straight line towards the y-axis. So this will give you a state line. That means you have identified one radioactive nuclide, and this will be the initial activity of the first radioactive nuclide. Now, how can you identify the presence of the other radioactive nuclide? So that means in this graph, you know the activity or the data of this curve, or you also know the data of this line because it is plotted on the graph, and you can any point you can find out the value of any point on this state line. So how can you get the value or the data of the other nuclide? So I'm just going to explain. So let's suppose this is the composite decay. So at each point, let's suppose if you minus, this is the 300. If you minus 300 with this is the value of 80. This is the nuclide which you have identified because this is giving you the state line. So 300 minus 80 will give you the value of 220, and this will be at this point. So you know you have uh, uh, you can get the first point by just subtracting the total activity from the this activity, and this will be the point of this one. Similarly, you can do, let's if I want to uh, calculate the activity at this point, I know the value of this point because this is indicated on the y-axis. I also know the activity of this point, which is the state line, because it is, I can easily get the value from the y-axis. And if I subtract this minus this, the value I will plot over here. And similarly, I can plot the points just subtracting a minus b, and this will you give the points at line C. So if it becomes a state line, or if, or another way I can say, if it give you a state line, that means another nuclide is identified. So two nuclides have been identified because you have two state lines on this semi-log paper. So similarly, you can, that means this composite decay is the mixture of two nuclides. And how can you identify which one is the longer lived and which one is the shorter lived? Just the half-life, you can calculate the half-life. Like here, the 80 is the initial activity, and 80, half of the 80 will be the 40. And if you have the 40, and this will be the connecting to this line, and if you move here, this is the 8, and 8 is the half-life. And similarly, this is a 200, half of one is a 100, and it will give you value over here. This will be around 0.8 hours. So that's why this is having the more half-life. That's why this is called the longer lived radioactive nuclide, or the longer lived component, and this will be called the shorter lived component. And similarly, you can calculate the initial activity over here. This is 200, this is the 80, and the half-life of the both nuclide. So this way you have analyzed the composite decay by just plotting the data on a semi-log paper. So just moving to a real calculation of the data I have used for your reference. So this is the data available. That means with respect to time, you will get the total activity. And this total activity may be the activity due to one component, or maybe the activity of the two component. Here, I have identified this activity, total activity, is the activity of the longer lived and the shorter lived. That means two radioactive nuclides are present in here. And now I'm going to analyze them and to identify the initial activity and to calculate the half-life of these both radioactive nuclide. So this is the, actually I have manually plotted this graph. I'm going to explain here. Let's suppose the first plot of this point at time 0.3 hours. The total activity is it is the 11,100. So zero point 0.3, it is very close to the zero. So I have plotted over point here. This is the 11,100. So similarly, 5870 at 5 hours. This is the 5 hour. This is the point at 5870. Again, 2340. This is the 2340 and 2205. Again, this is the, sorry, 2005. Similarly, this point is 1440, 1015, and this is the triple eight, and so on, 826 and 825. So I have just skipped few of the points just to make it clear over here. So this again, now this is giving you a curve, and curve is the indication that there are more than two nuclides, more than one nuclides are present. And this composite decay is the mixture of two radioactive nuclides. Now I'm going to separate them and to calculate their initial activity and the half-life. Again, first was the to plot the total activity. Now this you have plotted the time versus activity which was available to do. So these you have to calculate yourself. So let's suppose again starting with the first point, it is 11,100. And how can you identify the first nuclide? Just this is a straight line, and you can extrapolate this straight line towards the y-axis, and this is giving you a straight line. That means this is the line for one of the radioactive nuclide. So this is the initial activity, and you can calculate the half-life of this activity by using the same method. So first to calculate, so this is the one nuclide. Now I'm going to identify the second nuclide. So I'm just subtracting the values of this identified nuclide from the total activity points. So let's start with the first one. It is 0.3, and the activity was the 11,100 over here. And this activity is the a little bit more than 1000. Let's suppose this is the 1110. So how can you, because this is the longer life, because it is having the more half-life, you can designate is the longer life. The first identified will be the longer life, and second will be the shorter life. So how can you identify the activity for the shorter life? Just subtract the longer lived activity from the total activity. So this minus this will give you the value of 9,990, and you can plot over here. This will be the 9,990, very close to this point. So second point is at time 5 hour. It is the total activity was 5870. 5870. This is 5,000, and this is the point as we have already discussed before. And the at 5 hour time, the activity of this longer live is 1085, and the point is here 1085. This is the at 5. You can take a point from here and go to the line and then check what is the activity over here, and this is the 1085. And you can just now subtract 5870 minus 1085. it will give you the value of 5785. And this is the activity for the shorter leaf, 4785. And this is the 4000, and this is the point 4785. And similarly you can do for the rest of the points. So it is simply just to subtract the value of the longer lived out of the total activity of the composite decay. So let's have a look at another point. The last point is the time 30. As time 30 hour, the activity of total activity is 1015. It is here. And the activity of the longer live, this is the point. At the point, you can take here, this is the activity of the longer live, and this is the value of 980. So you just subtract 1015 minus 940, it will give you the value of 75. So 75 is like here it is because I have just taken at the starting with the 1000, so it will be little bit below. If you take a cycle starting with the 10, you can easily plot this point. So again, there will be no big change because it is very close to the 100. So I'm just taking the point over here. So this will be the point for the shorter leaf. So these points I have just plotted by subtracting the half longer lived activity from the total activity. So these are the points. So just have a just a plot a straight line covering all these points, and this will give you the line like here. So again, if it is come as a straight line, that means you have identified and other radioactive nuclides. So there is only the presence of the two nuclides. So now to calculate the activity, initial activity and the half-life. So first, this is the longer live. Why it is called the longer live? Because it is having the more half-life. So let's put this is this activity of the longer live is around 960. I just taking just to give you a more clear picture. At it will be at time 0 because our time is starting from zero point 0.3 hours, again very close to the 0. So this is the total activity, and you just take the half of this one. This will be the 480, and 480 is here, and you just extrapolate to the line and then move to the x-axis, and this will be the half-life, and it is 148 hours half-life for the longer live. And this is the initial activity. So you have analyzed the one radioactive nuclide. Again, by using this line, initial activity is 10140 at time 0. So divided by this one, because you are know this is the initial activity, and this is the activity when the time is half, and you can calculate the half-life by using this activity, and it is 5070, and this is around the 5070 over here. Sorry, 5070 little bit here, and this is the line coming down towards the x-axis, and this is the half-life of the other nuclide, and this is 5 hours. So that's why this is called the shorter lived, because this is having the small half-life or less half-life as compared to the other nuclide. So this was about the analysis of the radioactive mixture. So see the application of the Semilog paper, you are just putting a data and then analyzing how many nuclides are present. So in this case, there are two nuclides are present. So the question is, if there are, let's suppose there is more than two nuclides are present, and then subtracting the activity of the longer leaf from the total activity, and this line will give you a again curve. So indication of this curve is that there are more than two nuclides are present, and you can do the similar process to identify the third nuclide. So this is all about the analysis of the radioactive mixture or radioactive analysis of the radioactive decay. And if you want to learn more about the connecting videos, because in these videos, video one, I have explained the kinetics and the half-life. And in the second video, I have explained the detail about the Semilog graph paper and how can you draw or use the data on the Semilog graph paper. So these videos are available on my channel. You can just search by my name, or you can go to the website to have a look on these videos. Thank you for watching.